step down chopper with RLE load. The circuit is as shown. When the chopper is turned on, during this turn on period, the input voltage Vs is going to appear across the output V0. During the turn off, the output voltage will be 0, and again when the chopper turns on, the voltage appears. When voltage is appear across the RLE load, the current gradually increases from its minimum point to maximum due to the inductor present in the load. When it is turned off at T on, the current gradually decreases to minimum value and then it increases. This is going to repeat the next cycle. During the turn-off period, the current flows through the freewheeling diode. This is continuous conduction operation. At a low frequency and low output voltage, the load current may be discontinuous. The input voltage is going to appear across load and the current gradually increases to maximum value. When turn-off time is more, the current flows through the freewheeling diode and reaches to 0, and again chopper is turned on, the current gradually increases and the voltage across the load will be minimum of E in the discontinuous period. Then again the chopper is turned on. This is discontinuous conduction mode. Discontinuous conduction is going to depend upon the turn-off time or the time constant L by R. If the time constant is less than T off period, then you are going to get discontinuous conduction. During the chopper on period, that is T is in between 0 and T on, the current flows from Vs positive chopper RLE load back to Vs negative. And the differential equation governed by this is Vs equals to I1, so I1 while increasing, or plus L di1 by dt plus E. Taking Laplace transform for the above equation, you will be getting Vs by S equals to I1 of S of R plus L of S I1 of S minus I1 at initial stage, which is nothing but I1 at initial stage is I minimum, so I minimum plus E by S. Now solving this for Is, Vs minus E by S equals to I1 of S of R plus L S of I1 of S minus L I minimum. At this side, I1 of S will be common, R plus Ls minus L I minimum. I1 of S equals to Vs minus E divided by S of 1 by R plus Ls plus L I minimum divided by R plus Ls. At right hand side, Vs minus E by S. Taking L out of this, then you will be getting S plus R by L plus L I minimum divided by L S plus R by L. Let R by L in the above equation equals to some beta. Then I of S equals to Vs minus E divided by SL of S plus beta plus I minimum divided by S plus beta. Now this is S multiplied by S plus beta. Let's do some partial fractions. Then you are going to get the result as Vs minus E by R of 1 by S minus 1 by S plus beta plus I minimum divided by S plus beta. By taking inverse Laplace transformation, we'll be getting I1 of t equals to Vs minus E divided by R. So 1 by S is 1 minus 1 by S plus beta is nothing but e to the power of minus beta t plus I minimum e to the power of minus beta t. So in this equation, at t equals to t on, the I of t value is I max. I max equals to Vs minus E divided by R of 1 minus e to the power of minus beta t plus I minimum of e to the power of minus beta t. Let this be equation number 1. During chopper turn of time, that is the time between t on and t, the current flows through the freewheeling diode, then the source voltage Vs will be 0, then the governing equation will be R. Here I consider this as I2 plus L di2 by dt plus E equals to the source voltage is 0. Taking the Laplace transforms, that R I2 of S plus L into I2 of S minus initial value of I2 of S. When you observe the waveform, this is I max for I2, T on time, theta, and this is minimum value. Initial value is I max plus E by S equals to 0. Now this equals to R I2 of S plus L S of I2 of S equals to I max L minus E by S, from which I2 of S equals to I max L divided by R plus L S minus E by S of R plus L S. Taking the L out of the denominator brackets, L I max divided by L S plus R by L minus E by S L S plus R by L. And we have assumed that R by L is equals to beta. Then this will become I2 of S equals to, let's cancel, I max divided by S plus beta minus E by R of, after partial fraction you will be getting 1 by S plus beta. Taking inverse Laplace transformation, I2 of t equals to I minimum of e power minus beta t minus E by R of 1 by S is 1 minus e power minus beta t. The final value of E2 is I minimum. So you can write I minimum is equals to, sorry, this is I max. I max of e power minus beta t minus E by R of 1 minus e to the power of minus beta t. That is equation number 2. Substituting equation number 2 in 1 to get I max. When you solve for I max, you will be getting I max equals to VDC by R of 1 minus E minus T on of beta divided by 1 minus E minus T beta minus E by R. Similarly, by substituting 1 in 2, if you solve for I minimum, you will be getting VDC by R of E T on beta divided by E T beta minus E by R. By solving for this, keep T equals to T on equals to KT. In equation 1, T equals to 1 minus T minus T on, that equals to 1 minus K of T in equation 2. The peak to peak ripple current, that is delta I, equals to I max minus I minimum, that equals to VDC by R of 1 minus e power minus T on beta divided by 1 minus e power minus T beta minus e power T on beta divided by e power T beta. Now delta I equals to VDC by R of E T beta of 1 minus E minus T beta 1 minus E minus T on beta of E T beta minus E T on beta of 1 minus E T beta. That is equation number 5. Peak to peak ripple current. The condition for maximum ripple is given by d delta I by dt equals to 0. Now, when you do this, you will be getting e to the power of minus k tr by L minus e to the power of minus 1 minus k tr divided by L equals to 0. From which we will be getting minus k equals to minus 1 minus k. Solve for this, then you will be getting k equal to 0.5. So the maximum peak to peak ripple current occurs at the k duty cycle equals to 50. That is given by del I max equals to Vs by R of tan h of R by 4FL. Equation number 6. For 4FL is greater than R, then tan theta is approximately equal to theta, and the maximum ripple current can be approximated to delta I max equals to Vs by 4FL. The load current would be continuous if L by R is greater than T or LF greater than R. In case of discontinuous current, I minimum equals to 0, then equation 3 becomes I1 of T equals to Vs minus E by R of 1 minus E minus T, beta is R by L. And equation number 4 is valid for 0 less than T less than T2, such that I2 at T equals to T2, which is nothing but the final value, equals to I minimum, which equals to 0. Substitute here, the time is T2, then you will be getting minus E by R of 1 minus e to the power of minus beta is R by L of T is nothing but T2 here now, plus I max of E minus R by L of T2 equals to 0. Now, when you solve this for T2, you will be getting T2 equals to L by R ln of 1 plus R I max divided by E. That is the equation number 8. T2 is nothing but turn off time here.